she's quite happy being away from any chance of catching it.
Yeah.
So we got, remember, all she's doing, she's just decorating the new house and things like that. So yeah.
Hi, Andy.
Hello, who's that?
You. Who's that? You don't recognize me.
Yes, I do recognize your voice now. Yes,
it's a long time no see, but anyhow.
Yes. How are you?
I'm well.
Are you in Italy? Are you in Modena, or are you in?
Can be. What?
Are you in Modena or in Sao Paulo?
No, I'm in Sao Paulo.
Hard luck.
Yeah, in fact, I'm in Sao Paulo. You know that 1 year ago, I came from Modena to Sao Paulo, a little bit more than 1 year ago, because I had to be here for a while because I was head of department, and then I would go back. And then, you know.
Stuck. You're stuck here.
I'm stuck here ever since, yes. Yeah. So. Not even, yeah. And you know, our events are also, you know, it's a bit hard.
Yes.
Our international events, I mean.
Yes. Yeah. Everything is difficult. Yeah.
Everything is difficult. What can we do? We have to go on. We have to go on, to go on, to go on, to go on, to go on. That's it.
Yep.
Yeah.
So that's it. One of these days it'll have to go.
You have to go where?
No, the virus will have to go.
Oh yeah. It will have to go. It will have to go and not to change. Yeah.
One of the best pieces of research that they've just discovered is that the common cold, the common cold, which is a rhinovirus. Yeah, it displaces COVID. So if you've got COVID and you catch a cold, the rhinovirus kicks the COVID out of your cells.
Common cold.
The common cold.
Come in, be welcome.
Yeah,
where is it?
Where is your savior?
Where is this? Where did you find it?
University of Glasgow published it.
Glasgow?
Yeah, they published it a few days ago. It was on the BBC and everything.
Good, fantastic.
It's this thing about some viruses are happy to live with other viruses, and some viruses just want to live on their own and they'll kick everything out. And it just happens that the rhinovirus kicks out a SARS virus. So
good.
Yeah, there's things. People are finding these things out slowly.
Yeah. Good news out of bad news. Fantastic. Fantastic.
So,
and where are you?
We are in Newcastle.
Newcastle.
Yes, we moved house. In the middle of the pandemic, we moved house.
Newcastle.
Yeah.
Nice.
So I look out my window and I can see the classical concert hall across the river.
Show us. Move your.
Hold on. Let's see if you can see. Where are we?
How nice. How beautiful.
See if it'll come up.
Fantastic. Look at it. Look at
there
it.
You go. That's the concert hall.
Yes. Very nice.
Yeah.
Super
we live right on the river.
Nice, Andy.
Yeah,
fantastic.
We moved. Yeah. So it's a bit like being in Florianopolis on Beramar.
Yeah.
Quite similar to Beramar.
Very nice. Now we are seeing all your slides. You have to go back to the first one.
Okay. Well, because I had to take my big monitor out. There we go.
Good. Fantastic.
But then it's back again. Here we go. So yes, it's very different to living in the countryside of the frozen north. It's lovely and sunny and warm in Newcastle. It's great.
Newcastle is beautiful. Yeah. However, you know that I am in Sao Paulo. So nothing to do with countryside.
That's
So
right.
seeing
There's
a bit
nothing.
of green is good also.
Well, there's a little bit of artificial grass just down on the riverbank in front of the house. Or it's an old warehouse that's converted into apartments.
Converted into a?
Into apartments.
Okay.
So we have the whole top floor.
Wow. Wow.
It's great. So, but they're all down there on the artificial grass, sitting there, supposedly in lockdown. But then there's
it's beautiful, beautiful, beautiful. I don't have that. I see. I see, but I can see the wood. I can see the trees, and I can see a tray of trees, and that's it. Then
that's right.
Then apartments all next. But
that's right. I remember where you live in Sao Paulo. Yeah, it's pretty built up.
Yeah.
I said I remember where you live in Sao Paulo. It's pretty built up.
Yeah. And now the parks, the Ibirapuera is closed. And it was not, then it closes, then it opens, then it closes, then it opens, and that's it.
That sounds like Brazil. On, off, on, off, on, off.
No, don't say that. I hope we're going off this thing, and then we get back to being beautiful Brazil.
You will do.
BB, BB. Beautiful Brazil.
Beautiful Brazil.
Yeah. Brasil bonito.
If you get rid of a certain person in charge of the country,
if we get rid of certain persons, yes, that would be nice.
Yeah,
that would be nice. Yeah.
Yes. All right, guys, could we start? It is already 2 p.m.
Yep. I mean, we've got lots of people, haven't we?
Right. Yeah, there are. We were in around 200 attendees because we are also. People are seeing YouTube also. So it's really nice.
Good.
So let me introduce Professor Andy Monkman, and it's a pleasure to have you here participating in our meeting of the National Institute of Organic Electronics. And I know that many people here from the Institute already know you, and you are also a guy that are times to times here in Brazil, in conferences, in the SBP MAT conference. And I also used to say that you are almost a manezinho. Yeah, manezinho.
Getting better.
People know that manezinho is a kind way to say people that are born in the island of Florianopolis. And but so, Professor Andy is professor at the physics department of the University of Durham in England. He's director of the Photonic Materials Center and head of the Organic Electronic Materials Research Group. He coordinates many international cooperation projects, and actually we are also together, we participate in the European Union Horizon 2020 in the project called Organic Charge Transfer Applications. Yeah. And he has more than 560 publications, more than 23,000 citations. His H factor is 80. So, and publications in journals like Advanced Materials, Advanced Functional Materials, Nature Communications, JACS, and so on. And he is recognized to be pioneer in TADF materials applied to OLEDs. And exactly about that, he will talk to us today. And so thank you very much, Andy, for accepting the invitation for this talk in our meeting. Let me just tell that people can put questions here in the chat, in the Zoom room, also in YouTube. And at the end, I will transmit these questions to Andy. Thank you.
Thank you, Ivan. Can you see my little cursor on the screen?
Yeah, we can see it. Perfect.
Okay, because I'll use that to point. Okay. So boa tarde a todos. Hope everybody's very well. It's nice to be kind of back in Brazil, as close as I can get at the moment. So what I wanted to talk to you today is about where OLED materials are progressing and really what is the end goal for materials in OLEDs, especially emitters. And through the development of these new materials, how are we going to change how we manufacture OLEDs? So I'll come to that right at the end. So at the moment, everybody knows you can buy OLED TVs, and you can even buy these things now, these OLEDs that roll up out of a box and appear like magic. If you've got $90,000, you can buy one today. And I don't think many of us are going to buy one at $90,000. Okay. So everything looks at the moment quite good for OLEDs because commercial, you can buy them and they look very good. But there are some secrets in here. For instance, for this OLED, the blue is actually a fluorescent material. It's not iridium, right? And it's not a triplet emitter. It's a fluorescent emitter because there's no stable deep blue triplet emitter that they can use. So there's a major problem here because the efficiency of this blue is supposedly much less than the red and the green. I say supposedly because I'll tell you a dirty little secret later on about OLEDs. Okay. So for those of you who aren't too familiar with an OLED, it is very much like molecular Lego. Okay? So for almost all commercial OLEDs, all the materials in the OLED are small molecules and they are deposited from vacuum in very large scale vertical deposition systems. And there are a range of materials which go into this OLED stack, maybe up to 11 or 12, and they all have different roles to play in the function of the OLED. But basically, if you break it down, the key material sets that you use in an OLED, you have your anode and your cathode. So your cathode is typically a metal, aluminium or magnesium aluminium or something. The anode is indium tin oxide, the semi-transparent electrode. You then have a range of materials which transport charges from the electrodes to the active region where the light's generated. So you have materials which transport holes. You have materials which block electrons. So if you think about the hole moving through here into the emission zone, you have a blocking layer here which stops the hole going any further. And the idea is that if you trap all the charges in this emission region, you're going to get the most efficient recombination of the charges to form excited states. Okay. What we're particularly focused on in Durham is understanding the materials in these emission layers which actually convert the charge into excited states and give off light. So we're studying mostly the processes associated right in the middle of the device. Okay. And the key piece of physics that we're studying, we're trying to overcome, is the problem of how to deal with non-radiative excited states. So when an electron and a hole recombine, the two electrons here, because there's really an electron here, are not correlated. So when they join together, their spins are randomly oriented. And so statistically, you'll get 25% singlet states, which emit, and 75% triplet states. So 3 to 1, which are dark states. So of course, you've got to find ways of handling these triplet excitons to convert them into an emissive state. And what you really want to do, of course, is convert them across here to form the same kind of singlet state. So all the emission comes from the same state. So typically in OLED, commercial OLEDs at the moment, for the red and the green, this is done by iridium complexes, and it's basically a phosphorescence process. So in fact, what they do in iridium is they take the singlets and convert them to triplets, and everything comes out of phosphorescence. You can't do that with blue because the iridium complexes are intrinsically unstable in the deep blue, and they fall to bits. So they have no lifetime and they aren't used. So that's why, as I said, in that blue OLED TV, the blue emitter is actually a fluorescent emitter. So it's much less efficient than the red and the green. So if we can't use iridium for deep blue, is there another mechanism by which we can convert the triplets to singlets to generate light? And yes, there is. So way back, almost before I was born, but not quite, people discovered E-type delayed fluorescence. So this isn't triplet annihilation. This is delayed fluorescence that comes when the triplet state of a material is close enough in energy to the singlet state that you can get thermal excitation of the triplet to allow it to reverse intersystem cross back to the singlet. So this is a thermally activated intersystem crossing or reverse intersystem crossing process. And the key elements of this mechanism are how big this gap is, or rather, sorry, how small this gap is, so that it's easy to thermally populate up to an energy equivalent to the singlet, because the spin orbit coupling or the intersystem crossing here is isoenergetic. So you have to get up to here to allow efficient spin orbit coupling to bring you back to the singlet. So this mechanism was discovered by Parker in '64. Chihiro Adachi in Japan realized this would be good for OLEDs, and he was the first person to actually demonstrate that you could use this mechanism to harvest triplets in OLEDs, and he christened it thermally activated delayed fluorescence. However, way back in 1968, people are already calling it thermally activated delayed fluorescence. Okay, but this is the mechanism that we're going to study, this TADF mechanism. So, key element, we have to have a singlet and a triplet state in a material as close to each other in energy as possible to get the most efficient verse spin orbit coupling or reverse intersystem crossing. Okay, so the way that we do that is by effectively separating the HOMO and the LUMO. So in the excited state, the two electrons are completely decoupled from each other electronically. And of course, there are two ways that you can do that. You can either physically separate the HOMO and LUMO in space as far apart as possible, or you can have the HOMO and LUMO orthogonal to each other, so that again, there's no wave function overlap between the HOMO and LUMO, so that the two electrons don't talk to each other. Why don't you want the electrons to talk to each other? That's because the reason that the triplet energy of a material is less than the singlet energy is because of this exchange energy. So it's basically Pauli repulsion. So in the singlet state, where the spins point in the same direction for the two electrons, they have the same quantum numbers and they can't get close to each other spatially. It's Pauli via Pauli's exclusion principle. But in the triplet state, because the spins are opposed, then the quantum numbers aren't the same, and the two electrons can get much closer to each other without feeling any repulsion energy. So therefore, the triplet energy can be lower than the singlet energy because this Pauli repulsion is less. And we call that the exchange term J. So the difference between the singlet and the triplet state is twice J, twice the exchange energy. Okay. So we can see here, this is the equation basically for that exchange energy. And you can see it goes as 1 over the separation between the two charges. So if you pull those two electrons apart further and further, this goes to 0. Or if you make the HOMO and LUMO orthogonal, then this term is 0. And again, J goes to 0. And the singlet and the triplet are effectively the same energy. You have to be a bit careful doing this, because if you look at the transition dipole moment for the decay, and you look at this equation, you say, well, if you pull the two charges further apart, the dipole moment will go to 0. And if you make the two orbitals orthogonal to each other, dipole moment goes to 0 again. So maybe you have to be a bit careful, and by completely minimizing J, you might also minimize the transition dipole moment, and your quantum yield will be 0. But we find that that usually doesn't happen. Other things dominate the dipole moment, and there's enough coupling for over long lifetime that you can have very high quantum yields. So the best way to achieve this situation is going to a charge transfer state where you naturally have separated the two charges, the two electrons in the excited state. And by going to this orthogonal picture, you can have a small molecule and still effectively separate the charges or decouple them very strongly. So let's have a look at how we do that. So this is one of the first molecules that we started to look at. And you can see the date, it was 2013, a long time ago now. And what we found is that this material, which is made of two donors, two carbozols, joined to this SS dioxide. So it's this thiophene SS dioxide unit, which is an acceptor. So we have a nice charge transfer system set up. You have the LUMO and the HOMO, and the LUMO and the HOMO are well separated from each other, so they're decoupled. And if you do a calculation, changing this torsion angle between the donor and the acceptor, you see that as the torsion angle goes to 90 degrees, so the donor and acceptor become orthogonal, the energy difference between the singlet and the triplet goes to roughly 0. In this particular material, we found that actually the gap was about 0.28. It was very big, but it was just small enough that we could see a little bit of delayed fluorescence. This material, however, is much, much better. So this again is the same acceptor, the SS dioxide, but now we have a phenothiazine donor, two donors again. And what you find is that naturally for this material, the donor and the acceptor form completely orthogonal. It's about 89 degrees angle between the donor and the acceptor. And it's wonderful. So that it naturally forms a very stable, very strong charge transfer excited state. So if you look at the absorption and emission, you see that here the absorption of the molecule in black is effectively the sum of the absorption of the donor in red and the absorption of the acceptor in blue, so that they are decoupled. So effectively you have a separate donor and acceptor. But in the excited state, you have emission coming out here of the molecule, which is the CT state, which is much redshifted compared to the acceptor and the donor emission if you just measured them on their own. So this material forms a very nice CT state. And the beauty of it was for us that it formed a very beautiful CT state, even in a completely non-polar environment like MCH solution. So we could do lots of studies and understand this material in detail. If you do electrochemistry, you can see again that the donor and the acceptor are effectively electronically decoupled. So the electrochemistry of the molecule is in black. The oxidation of the donor is in red, and the reduction of the acceptor is in blue. And you can see that the oxidation of the molecule and the donor are identical. There's a little bit of a shift in the reduction of the acceptor, but basically, again, in the ground state, the donor and acceptor are decoupled because they're perpendicular to each other, and they form a very strong CT state in the excited state. Okay. So if we have this TADF mechanism working to bring triplets back to the singlet state and emit, then when you excite the material, a certain proportion of the fluorescence that you measure comes from states which were triplets for some of their lifetime. And you've harvested those triplets back to singlets. So if you do a very simple experiment here, so this is in MCH solution. In black is the emission when you degas the solution, and in red is the emission when you leave the oxygen in the solution. And you can see you get nearly 12.5, we get more than 12.5 times more fluorescence when you degas the solution than when you leave the oxygen in there. So that's telling you that the oxygen, which is quenching the triplet excited state, is getting rid of something like 90% of the triplets. And so in the degassed case, the black, something like 92% of all the states which emit, which must be singlet, at some point in their lifetime were triplets. So you're harvesting all these triplets back by this hopefully this TADF, this thermally activated delayed fluorescence mechanism. And the PLQY in air is 3%, so aerated solution. In the oxygen-free solution, the PLQY went up to 33%, so 10-fold increase. It's this. Right. I'll put down here, remember this number, we'll come back to it. So you can see that you can prove that a very large proportion of the emission that comes from these TADF molecules do come from triplet states, because you can simply quench them by oxygen and wave bye-bye to all your emission. Okay. Another way to do this, to prove that this delayed mechanism is most probably TADF, is by doing a power dependence. So that's of the excitation power, the laser source in this case, of the delayed emission. So we measure the delayed emission. So we use a intensified CCD camera, gate out all the prompt emission, and just look at the delayed fluorescence. That should be the emission that comes from the triplet states that come back to the singlet. And you can see we get beautiful linear power dependence. We get a linear power dependence in solution, get linear power dependence in solid state. So that means that the emission that's coming from the delayed fluorescence is a monomolecular process. It's not a bimolecular process, such as triplet annihilation, because that would give you a quadratic excitation power dependence. So you can differentiate between these monomolecular TADF mechanisms and the bimolecular triplet annihilation mechanisms. So let's have a look at the photophysics of these TADF materials in more detail. So if we do it again, use gated time-resolved emission and look at what happens to the emission as a function of time. So we see in the first few nanoseconds, we get emission coming out of the donor at the same time as getting CT emission, because the electron transfer, the charge transfer step is so slow in these materials because of this very strong decoupling of the donor and the acceptor in the excited state. And then for this particular material, you see that there's quite a strong relaxation of the CT state over time. So over something like 14 microseconds, this CT, the energy of the CT state shifts quite a lot to the red. But this is all the delayed CT emission. And right here in the first few, say 50 nanoseconds is the prompt CT emission. So another way to look at that, in this, if we look at this plot first on the top left, is we look at the integrated emission under each spectra that we time resolve. And so in the first 30 nanoseconds, we get prompt CT emission. So that's a singlet CT state that never crossed the triplet manifold and decayed. Okay? And then this region from about 50 nanoseconds to, in this case, 5.5 microseconds, it might be a lot longer in other cases, we get this region where we effectively get time-dependent intensity. And this is the delayed fluorescence. The spectrum that emitted here is exactly the same as the spectra emitted here, but it has a much longer lifetime. And as we cool the sample down, you see that that intensity decreases. So you can see that this delayed emission is thermally activated. And as you cool the system down, you get less of this delayed fluorescence. So that shows that there's some energy gap, and you have to supply thermal energy to overcome that energy gap. Interestingly, for this particular material, is that if we look in this region where we get a crossover between delayed fluorescence and actually phosphorescence, you can see that as you cool the system down, the intensity increases. Right? But this is pure phosphorescence, and that's well known that as you cool the sample down, the phosphorescence gets stronger. So you can see all the mechanisms that are going on in the decay of this molecule by using this gated time-resolved emission mechanism. And this at the bottom just compares the room temperature emission decay profile between 1 nanosecond and about 10 milliseconds. This is room temperature, where you get this huge delayed component. And in the red is 80 Kelvin, where virtually all of this delayed fluorescence has disappeared. So that's how strongly thermally activated that delayed mechanism is. And the way that we calculate the rate of this reverse intersystem crossing is to use a simple kinetic rate model for the rate of formation and decay of singlets, triplets. And we use a very simplified picture. We found that this picture of basically we excite a singlet, some singlets decay, some singlets cross to triplets, those triplets come back and they decay, is good enough to fit the decay profile that we measure. And we get, very nice fits to give us the prompt radiative emission rate, the intersystem crossing rate, and the reverse intersystem crossing rate for these molecules. So for this particular one, the reverse intersystem crossing rate is 5×10⁵ per second, which is moderately quick. It's not that fast, but it's fairly fast. Okay. The other important thing to be able to measure and understand is the triplet states. So we look at very long decay times, and also probably we cool down to 80 Kelvin or even 20 Kelvin. And in this 10 to 100 millisecond regime, we see a new emission. Hopefully it's structured, which shows that we're actually looking at a local excited state decaying. On such a long lifetime, this must be phosphorescence. And what we find is that for a lot of materials, we actually get dual phosphorescence. The black is the phosphorescence spectrum of the CT molecule. The blue is the phosphorescence of the acceptor part. The red is the phosphorescence of the donor part. And you can see that we have a very good linear combination of phosphorescence from acceptor and donor coming from the CT molecule. And so the lowest triplet energy of that molecule is the energy of the donor here, not the energy, the onset energy of the phosphorescence that most people measure and claim is the triplet energy. And so this gap that you measure from comparing the phosphorescence to the CT emission, okay, is the difference in energy between CT and a local triplet excited state. It's not the energy difference between the CT singlet and the CT triplet. That's a big confusion that a lot of people have in the literature. This is what you measure optically. And for this material, this gap is down to about 20 millielectron volts, which means that this gap is a lot smaller. But you can see you've got very small gaps between your singlets and triplets. So that's why the TADF is very efficient. So that's good. So you take this material, you make a fairly simple OLED structure with it, and you can get efficiencies of nearly 20%, which means that you're effectively harvesting all of the excited states, both singlets and triplets, that you generate from charge recombination. So this TADF mechanism can give you very, very high efficiency OLEDs, nearly 100% internal quantum efficiency. Now, for this particular material, we're looking at somewhere in the region of, as I said, nearly 100% internal quantum efficiency. If you use your equation to work out what the external quantum efficiency that you measure, 19%, should be, and we put the PLQY that we measured for that material, 33%, into that equation, then the EQE should only be 9%. But the EQE of the device that we measure is 20%, which implies that the photoluminescent quantum yield of that material has to be at least 65%. So why are they so different? What's suddenly gone wrong with understanding these OLEDs when we're already assuming that everything else is almost perfect? It took us a little while to fathom that one out. We got the idea of what was going on from the electrochemistry, because the electrochemistry, right, when we oxidize the donor, that's taking the electron off. When we reduce the acceptor, that's putting electron onto the acceptor. So when the charges come to this molecule, right, the electron goes onto the acceptor and the hole goes onto the donor, and you generate a CT state immediately. You don't generate an excited local state, you already generate the CT state. You avoid going through any excited state just on either a donor or an acceptor. So if you look very hard at the absorption of this TADF molecule, right on the very edge of the absorption below the pi-pi star transition, there is another transition. It's quite weak. The extinction coefficient is only of order between 100 and 1,000 per mole per centimeter. But if you come in and excite on this transition, you produce beautiful CT emission, because this is the direct CT transition of that molecule. And if you measure the quantum yield of exciting that molecule via that direct CT transition, you find out that the PLQY goes up to 65%, because you're avoiding losses associated with having a local excited singlet state, which is actually crossing to the triplet manifold. So what we know is that during charge recombination in these TADF OLEDs, when the charges recombine on your TADF molecule, they generate the CT state immediately, and that CT state decays with a higher quantum yield than if you first excited a local transition, which then had electron transfer to form the CT state. So this is why you get very high efficiency devices, because of this way in which you generate the excited states via direct CT formation. Okay, so let's have a look a little bit more about this actual TADF mechanism. So because you've got a charge transfer state, you've got a very large a very large excited state dipole moment in the molecule. So if you put that into different polarity solvents, you can make that excited state relax enormously. So for this particular molecule, you can go all the way from a local transition in nonpolar to a beautiful Gaussian CT state in polar solvent. And this is the solvatochromic shift. And all of these TADF molecules, because they have a very strong charge transfer character, show this solvatochromic shift. So it's hard to see in this plot, but this is our molecule in, let me find it, a very non-polar polymer, ZNX, emits in the blue. In toluene, you can see you get a very large shift just by going to toluene, where the polarity is quite low. If you go to methyl THF, which is very polar, then you get a very strong shift, and you also get a huge amount of quenching of the emission. So you get very strong subatomic shift in these TADF molecules. What we found was if we put it into a polyethylene oxide solid film, the polyethylene oxide has a strong dielectric coefficient. So it has a high dipole moment, which interacts with the CT state of the molecule. And as you cool it down and the polyethylene oxide starts to crystallize, you see that the emission from the CT state of the TADF molecule that's doped into that polyethylene oxide also shifts. And at room temperature, it's here, quite red. And at 150 Kelvin, it's way over here, much bluer. So if I plot that out, this is what happens to the CT energy as I cool the system down. So I'm basically tuning the CT energy with temperature. If I then measure the delayed fluorescence intensity from that TADF molecule as a function of temperature in this polyethylene oxide matrix, I can see that as I cool it down, initially the delayed fluorescence increases. As I cool it down, it reaches a peak and then it drops off again. So as I cool it down further, I get less and less emission. This is what the CT energy is doing. So the CT energy is getting bigger. The local triplet energy of that molecule, because this is the local excited state, it doesn't feel this change in the environment due to the polyethylene oxide, and it stays at exactly the same energy. And you can see that when the CT energy coincides with the energy of that local triplet state, you get a maximum of the delayed fluorescence. And if you go away from, if the energy of the CT state gets larger or smaller than the local triplet state, then the DF intensity decreases. So basically, what we found was that the DF mechanism is maximized when the one CT energy, the singlet CT energy, is resonant with the triplet or the lowest energy local triplet state. So this local triplet state is very important in generating this thermally activated delayed fluorescence. Right? And it's so important that you can see that it's actually more important than the thermal energy, because to start with, the DF goes up as you cool the system down. So this is the key to understanding the actual mechanism of thermally activated delayed fluorescence. So in fact, what we found out is that the actual mechanism for generating the delayed fluorescence is second order vibrational coupled spin orbit coupling. Right? It's a very long name. I'll explain it very quickly. In a way, the key to understanding this is understanding that for the CT state, the one CT, if you make the one CT and the 3 CT, the triplet CT state, to be completely decoupled, so they're exactly the same energy, they also have exactly the same orbital. So therefore, you can't have a spin flip going from the singlet CT to the triplet CT, because you can't change your orbital angular momentum anymore because they're the same orbital, they're degenerate effectively. So this transition between singlet CT and triplet CT is forbidden when the energy of the two states is the same. And of course, we're working very hard to make the energy of these two states the same to maximize the TADF. So this direct spin orbit coupling between these two singlet and triplet CT states is forbidden. So we need a third state to help. And what we need that third state to do is mix with one of the CT states to make its orbital different enough that you can then have change of orbital angular momentum going from here back to the singlet. Right, so this is spin vibronic coupling. This is quite well known. And so for this particular TADF molecule, this is the acridine donor, and this is the XTN acceptor. The very strong vibration of this double bond oxygen perturbs the whole of that molecular structure. And so at some point in the vibration, if you like, as that molecule changes its shape, the triplet charge transfer state and the local triplet state have the same configuration, and they cross. And when they cross, they're effectively strongly mixed. And then that allows the spin orbit coupling to take you back from the triplet manifold to the singlet manifold. This is how this spin vibronic coupling works. Okay. So for our TADF molecules, work with our colleagues in Newcastle, Tom Penfold, we calculated the energy surfaces of the singlet and triplet CT state and the lowest energy local triplet state. We apply vibronic motion and we calculate the dynamics of this molecule and how the energy surfaces change as the molecule vibrates. And you can see you get crossings. So with certain vibrational modes, the LE3 and the CT3 mix very strongly, especially this one here, which is the torsion of the acceptor. It's very easy to get mixing between the triplet CT and the local triplet state. And then that mixing allows the triplet CT via this local triplet state, which acts as an intermediary, allows you to cross back by spin orbit coupling to the singlet CT state. If you didn't have this intermediary state that mixed, then this would be zero, because 1 CT and 3 CT would be effectively the same orbital, no spin orbit coupling. And it's second order because you need a bit of thermal energy, the vibration, to cause that mixing in the first place. That's where the thermal mechanism comes in. So to say that it's thermally activated is a bit wrong, because you're not using the thermal energy to cross you over a barrier. You're actually using the thermal energy to mix these two states. And when these two states are mixed, the vibronic strength is huge. So you get very efficient reverse intersystem crossing in these systems through this second order process. So that's why the local triplet, being very close in energy to both the singlet and triplet CT state, is very important to get efficient TADF in these materials. Okay. So if we just took hyperfine coupling between donor and acceptor, the risk rate would be negligible. If we had no vibronic coupling, so we have vibronic coupling, but very large energy gaps between the triplets and the singlet, you get pretty low risk rates. As that gap gets smaller and you have vibronic coupling, you can get much more efficient risk rates, approaching the risk rates that we get experimentally. So it shows that this vibronic coupling and the small energy gaps are both really important to give you strong TADF. Right, so let's go back to blue. So I said that this blue is generated by a fluorescent emitter, not an iridium. So we want to see if we can use a TADF emitter to replace the blue fluorescent in the device. So this is a blue emitter that we made in Durham, which is acridine and RSS dioxide again. When we measured it first off in ZNX, ZNX is the polymer you make compact discs out of, we actually found that the energy gap was quite large, which wasn't very good news. It showed this delayed fluorescence component, but it wasn't brilliant, and it was you can see that it gets quenched very quickly as you cool down. However, when we put that same material into this phosphorus containing DPEPO host material, we found that the energy gap decreased a lot. It went down to about 50 millielectron volts. And now the DF is much stronger. It's about an order of magnitude more delayed fluorescence. And the delayed fluorescence decays much faster. So the risk rate is really much faster. So by changing the host from the polymer to the DPEPO, we improved the reverse intersystem crossing by at least an order of magnitude, if not more. And we originally thought that was because DPEPO was polar and this was in a polar matrix. We've since done a lot of work to say that there is no such thing as solid state sulfatochromism, because sulfatochromism is just the solvent molecules rearranging around this excited state molecule, which can't happen in solid state. So this is just packing forces. This small molecule packs this TADF molecule in such a way that it minimizes the energy gap between the singlets and the triplets. Yeah. So in DPEPO, we find that the PLQY goes up to about 95%. It's incredibly efficient, very fast risk. The risk is so fast that oxygen really doesn't have much time to quench it in the solid state. So we don't have to make these measurements in vacuum anymore. We then put that blue emitter into a device, and we're getting somewhere in the region of 22% external quantum efficiency, which is again 100% internal quantum efficiency. We did have some problems with the emission shifting a bit to the green, and we found that was because these excited states were interacting across these layers, and we had to increase the thickness of this DPEPO layer to stop the emission layer seeing this layer here. So they were interacting and forming different exciplex states, which gave a green tail. So that the device structure is very sensitive to controlling the color. But we could make devices which were emitting at a peak wavelength of 450 nanometers at effectively 100%. So we thought that's it. We've cracked the blue problem. There it is, 100% efficient emitter at 450 nanometers. That's fantastic. However, everything else is fine. The device characteristics are beautiful. You don't get large loss of efficiency when you run at high brightness. Turn on voltage is very low, just what you want. The problem is that this emission is way, way, way too broad. It's about 70 to 80 nanometers, full half width maximum. To make a display, you have to have saturated colors. So the red, the blue, and the green have got to be about 20 nanometers broad emission peaks, because otherwise you can't then effectively mix them to make yellow or orange or other colors. So the dirty little secret in OLEDs is that they apply filters to their pixels to make the emission much narrower. And they end up throwing away maybe 70% of the light generated just to get a saturated color. So instead of the external quantum efficiency being 20%, it's more like 7 or 8%. And that's true for iridium, TADF, any other emitter, apart from a fluorescent emitter. So we've got this problem now. TADF works, but the emission is way, way, way too broad. You can't use it in a real display. It's impossible. So very briefly, how do we solve that? So this is the latest generation of materials that have come once they come onto the market, come into the research area. There are these what are called multi-resonant TADF emitters, and they contain boron and nitrogen. And because you've got boron and nitrogen, the HOMO is localized on everything but the boron, and the LUMO is localized on everything but the nitrogen. So in fact, the HOMO and LUMO are 90 degrees out of phase. So they're effectively decoupled. So the HOMO and LUMO have very little wave function overlap in these molecules. So they look like a charge transfer state. But when you look at their characteristics, they're actually beautifully excitonic. So this is the absorption spectrum of this molecule called VDABNA. You can see how narrow this absorption, lowest energy absorption is. If you look at the emission is incredibly narrow. So the full width of half maximum is about 20 nanometers. It's absolutely ideal for a saturated blue. But when you look at the actual properties of this molecule, it does give you delayed fluorescence. This is the delayed fluorescence component from this molecule, but it's very slow. You see the delayed fluorescence is going way out to nearly 100 microseconds. And if I do the oxygen experiment, you can see that the difference in emission between degassed and oxygenated sample is quite low. So there's not a lot of DF. The actual main reason for that is because the photoluminescence quantum yield is 90%. So most of your excited states, when you do an optical experiment, decay so fast from the singlet that there's hardly any triplets created. And so you don't get much contribution from the delayed fluorescence, but its lifetime is long. That's not what you want for a device. We also found out that this reverse intersystem crossing rate coming from this molecule is virtually independent of whatever you put it in, independent of any solvent, independent of any solid state. It's always around 3 to 4, 10 to the 5 per second. We also, when we look at the triplet state, we find that at 80 Kelvin, the energy gap between the singlet and triplet is less than 10 millielectron volts, but at 20 Kelvin, it's actually 70 millielectron volts. So in fact, what we've discovered is the way in which the triplets are harvested in these MR TADF systems isn't this CT, second order vibronic coupling. It's much more simple upper state triplet crossing. So the thermal activation is from T1, which is a little bit below S1, up to Tn, some excited triplet state, which is isoenergetic with S1, and you get reverse intersystem crossing. So the only part which is thermally activated is this reverse internal conversion. This orbital is completely different to that orbital, so the spin orbit coupling this way is allowed. So it's upper state triplet crossing, and that's why it's quite slow. The process is much slower than in the normal TADF materials. But they do make lovely devices. So you make a device with this material. It's very blue. It's not blue enough, but it's very narrow, 18 nanometers half width. So this is a perfectly saturated blue. The problem with the fact that the risk rate is very low means that as you increase the current to get more and more brightness, you lose efficiency very quickly. So the roll-off of an efficiency is poor. But you can get amazing external quantum efficiencies from these devices because those molecules are big, flat planar molecules. They tend to go down onto the substrate flat. They're aligned with their long axis parallel to the substrate, so that most of the light that they emit gets out of the device. It doesn't get trapped in the device by total internal reflection. So you get a huge outcoupling enhancement because these molecules orient preferentially in the plane of the substrate. So the external quantum efficiency can be as high as 35%. So they're fantastic, apart from this roll-off problem. So what do? You use this new process called hyperfluorescence, whereby you mix a TADF emitter. So this is the TADF emitter, one of our super blue materials, which emits here. And you mix in a bit of this VDABNA at about 1%. You get fantastic force to transfer, and all the light comes out of the V dampener. When you make a device, the TADF molecule is the host, which generates virtually all of your excited states, singlet and triplet. They transfer by Forster and Dexter transfer to the V dampener, and all the light comes out of that 1% V dampener. So all the light comes out with this very narrow line width, as opposed to the very broad line width you get from the normal TADF host material. So you can see the blue is a lot more saturated than here. And because you're using a fast, the TADF is the fast mechanism for converting the triplet to singlet, you get much less roll off. So out here, where it's still at 4,500 candelas per meter squared, you've still got an efficiency of 25%. So this is where we're going. And one of the main reasons you really want to do this mixture is because now the charge recombination is kept away from the emission. So all the charge recombination happens on that TADF molecule, which likes to have electrons and holes on it. It likes to be oxidized and reduced. Whereas this fluorescent molecule, if you put an electron and a hole onto that molecule to get recombination to an excited state, it usually won't like to be reduced, and it thermally degrades, or sorry, it degrades. So this is solving a lot of problems. Okay. So this is where people are going at the moment, these kind of hyperfluorescent devices using TADF hosts and these very narrow line widths, MR TADF resonant emitters. Okay. So this is basically the last slide. Why am I doing this? Why do I still want deep blue? And it's because, as I said, you need the saturation to be able to get good color mixing to make the biggest color gamut, or the whole range of colors for your display. At the moment, they use, this is the CIE curve. So this is all the colors that you could, your eye, or the perfect eye, can see. And this triangle is all the colors that you can generate by having this green emitter, this blue emitter, and this red emitter. So everything inside the triangle you can generate, everything outside the triangle you can't generate. And you can see this is pretty perfect. If you change the green emitter, you're not going to get any more colors. What you've got to do, you've got to cheat. You've got to have the blue way out here, and this part of the light that's generated, you can't see. However, it allows you then to have a much greater CIE, much greater way of generating all the colors in the CIE curve. So the area inside that triangle is much, much bigger than the area inside that triangle. So we want this blue way, way, way down in the blue here to be able to do this trick of getting much, much bigger range of colors out of the display. And then the way we make the display, this is the final thing. This is where we're all leading to. Your OLED display will then be made of just simply blue pixels. We can get an efficient enough blue with a long lifetime. The whole back plane, the whole light generation becomes a blue OLED. And then to make the red, green, and blue pixels, you have a red down converting fluorescent filter and a green down converting fluorescent filter. This can be 100% efficient. The blue comes out, it's saturated, right? These are producing red and green at 100% efficiency as well. So the whole display is effectively 100% efficient, but it's only made of one color pixel. You don't have to make red OLEDs, green OLEDs, blue OLEDs. You just make blue OLEDs. Okay? So this will make the production yield for the OLED much, much better. And so it will make them much cheaper and much easier to make. They'll have much bigger, better colors, be much brighter. So this is what's driving everything to make much better blue. But that blue has to have very well-defined characteristics to be able to do this, especially this saturation is very narrow line width. So that's where we're going. We're getting there slowly with OLEDs, but there's still a huge amount of work to do to get an optimum blue to allow us to make the optimum OLED display. And that's where we're going now. So that's it. Thank you very much for listening. Obrigado por ouvir. And let's have a look at the questions.
Hi, Andy. Wow, thank you very much for this fantastic talk. And you know, it's always impressive for me to see your presentations in first place of the new ideas that you always present, and the fantastic infrastructure, experimental infrastructure that you have to see, to measure really small differences. Yeah. And the third point is the interpretation that you have when you see that spectrum. And
thank you.
This is really incredible. Yeah, we have some questions here. Let's start with Rafael Santos. He says, "Thank you, Professor, for the presentation. I was wondering if you could say something more about the OLED's working stability and performance as a function of time."
Okay, that's one of the very critical parameters that all companies want. One of the problems with just TADF molecules is they don't have lifetime. There's a real problem with getting lifetime. If you go to the hyperfluorescent system, sorry, let's go back that way. So if you go back to this system where you separate the TADF and the emission coming from the fluorescent TADF material, the lifetime improves a lot. So what we think is that if you stop charge excited state quenching on the TADF molecule, then the lifetime goes up a huge amount. So basically you've got to get the excited states off of the TADF molecule as fast as you can onto this fluorescent emitter. So you avoid the exciton polaron quenching, which is what's giving you low lifetime. So that's one of the things that this hyperfluorescent type system of operation gives you an extra benefit. It does improve the lifetime.
Yes. Oh yeah, we have many questions here. Let me see. We have one of Gustavo. He's a PhD student in Florianopolis. He works with synthesis, and he is interested in synthesizing compounds with delayed fluorescence mechanism and liquid crystal properties. So his question is, how can charge transfer states affect the TTA mechanism? And he would like, yeah, basically that.
Okay, so to get the most efficient triplet harvesting, TADF, on the molecule, you've got to get your energy levels just right so that all three, the singlet CT, triplet CT, and whatever third state allows the coupling for the spin-orbit coupling mechanism, doesn't have to be a local triplet state. It can be another CT state, as long as it's very close and you can mix those two states. So you need that. You've got to avoid the lowest triplet state of the molecule to be too low. Otherwise, all the triplets just go straight down to that triplet state and do nothing. You can't get them back. So that's why in the ideal material, all those energies are the same, and there's nothing below it to stop the light coming back. To make them liquid crystalline, then you just got to obviously get shape anisotropy. So these kind of, where are we? These MR TADF molecules, which are starting to be long and almost ribbon-like, people even call them graphene ribbons, then these self-orient. So they start to have some kind of liquid crystalline property. This is why you get this very strong outcoupling enhancement, because the way that these molecules orient as they go down onto the substrate, they go down flat. So the transition dipole moment is out of the OLED, not into the OLED, and you get more light coupled out of the OLED. So these are really quite interesting. Understanding these molecules is not easy. They are not simple molecules to understand in terms of the photophysics and the physics of these molecules. Now, we've just published a big paper to try and start to understand the photophysics of these systems, but they're not CT, but they do CT-like things. They're quite strange. Okay, so for synthesizing something which is a cross between a liquid crystal and a TADF molecule, yeah, these are quite fun.
Yeah, really, this is interesting because of this possibility of aligning these molecules, and then you can the outcoupling. You can increase the outcoupling.
Yep, yeah, very important, very key performance indicator of these molecules. That's why they're really starting to get used a lot now.
Yeah. Well, we have a lot of questions here. I have to select some of them because of time. But let's see. Professor Osvaldo de Oliveira say thanks, Andy, for this fantastic lecture. And his question is: when TADF is used in commercial devices, what will be the consequences for the consumers?
The consumer will not know what is inside the panel. The consumer only sees the light.
In terms of costs, maybe.
Well, when we get to this architecture for the display, just using blue pixels and down converting filters. So this is called a hybrid quantum dot OLED type display. Then you'll see a huge decrease in the cost because the panel will be much, much cheaper to manufacture, and the panel yield will go up from like 10% up to maybe 80, 90%. So this is why this is the roadmap. LG, Samsung, all the Japanese, all the Chinese companies. This is the roadmap for the next generation of OLED of display panel. Okay, that's when you'll see the difference in your pocket.
Yeah, perfect. Okay, it's a good news. Yeah, the price would go down.
Yeah.
So here, Professor Faria is talking. Pleasure to have you as invited in our institute, and thanks for the excellent talk as we were expecting. Could you tell me if light emission can come from an oriented chromatophore can be linearly polarized? Could singlet or triplet states have any influence on the polarization of emitted light?
Okay, no, you can't get linearly polarized light because the molecules go down flat on the substrate. Yeah, but you can't control which way round they are. So these Dabner molecules go down flat, but they can go in any orientation in that plane. So there's no sense of orientation in the plane. So there's no linear polarization. People are going back to making circularly polarized emitters. They're using things like helicenes. So this is effectively bent right round and twisted to become chiral, and then they can get circularly polarized light. And people are starting to make circularly polarized TADF emitters, which does the same thing. You can then effectively get rid of one of the polarizers on the display.
Right.
Okay.
Yeah, thank you. Let me see here, Professor Cremona. He asked about the deep apple. You call this as a conformational effect?
Yeah, we've been doing a lot of work to try and understand what these solid state hosts do. Okay? So we've been studying materials that can't. So what the ones we've been looking at the moment are the Spiro TADF materials. So we have a Spiro bond between the donor and acceptor. So they can't move, they can't do anything, they're rigid. And we use that as a probe of what's going on inside the environment of the small host. So people say, if the dielectric coefficient goes up, then the host is more polar, but it isn't, because when I put that Spiro molecule into these different hosts, there's no change. There's no such thing as solid state sulfatochromism. It's wrong. Yeah, there may be some polarizability effects that people are starting to think about, but they'll be small. But what we can see is that the amount of free space in the host really affects what the emitters can do, and the way in which the host packs. So if you've got like a ball-like host, it doesn't pack very well, and the TADF molecule can move. But if you've got something which is really rigid, it packs really well, it locks everything in. So this is what we're discovering now these hosts do, is packing effects and those kind of changes. It's not solid state sulfatochromism. Yeah.
Right. Yeah, he also asks if the devices you present, if they were fabricated with co-deposition, and also if using blue as only emitter and filters, if we are going in the direction of the old LCD displays.
Yes, these are done by triple or double and triple co-deposition. So our big Leska system allows us to do triple deposition controlled. Just that's it. That's it. We can't do 4 materials unless you kind of cheat, but we can do 3. No, we're not going back to LCD in a way, because this is the big difference. Where's my blue film? Right. In LCD, the light engine produces white and the filters are subtractive. Yeah. So that the red filter throws away 80% of the white light generated. So the LCD is very inefficient. What we're doing here is we're only generating blue light, and the blue light is getting converted at 100% efficiency to green and red. So this is additive filters. So the overall efficiency is still very high. So that's the difference between this mechanism and an LCD. Yeah. Now you can see why you want to go this way. This is why people are desperate to get this.
Very, very clear. Just one interesting question of Professor Maria Luisa. She also says, nice presentation. She wondered if the almost UV light will damage eyes on TV.
Well, it's not. No, I mean, we're not really producing UV. Where am I going? That way? No, wrong way. You should look at that screen. Because we're down here, that the onset is pretty sharp at 450 nanometers. UVC, the lowest UV starts at 400. So you're still well away from 400, right? So this is safer and better for you than using a gallium nitride LED. So because in the normal LCD TVs now, they use a 400 nanometer gallium nitride laser or laser diodes as a light source. And of course that is 400, and that is more dangerous, and it's bad for you because it keeps you awake. The blue light really keeps you awake. So we're pushing away from that, and we don't generate anything in this 400 to 450 nanometer region. This has got to be shifted a bit. This is still not far enough to the blue. We need it to be about peaking somewhere around 455, 450 maybe, to be able to do this. All right. But this bit, they might even put a filter on this bit just to cut this off, so you don't, it's just not there to be able to get this much bigger color gamut. And the reason you want this much bigger color gamut is because of high definition TV and 4K and 8K. You can generate a much bigger color space with those big panels at high definition, and they want these colors to make the displays more vivid and brighter, and then they can charge you more money for them.
Yeah. Oh, so. Yeah. Sorry, people. There are still a lot of questions here. Some questions, but I think we have to finish because we have a next poster section now. And but I would like to thank you, Andy. Thank you really for this really interesting presentation. It was a pleasure to have you in our meeting of our Organic Institute, National Institute here in Brazil. And yeah, we hope to see you soon here in Brazil in the conferences, and when you are in Florianópolis, we can go for a beer.
Definitely. Thank you for inviting me. It's my pleasure. And we'll be back. We have to come back to see how the apartment is in Florianópolis. But we'll be back when we can. And I'll hold you to a bottle of wine and a few caipirinhas.
Exactly. So yeah, thank you very much. And yeah,
thank you. It's my pleasure.
We will be in contact.
Yeah, it's nice to see everybody again. Ciao, everybody.
Bye. Ciao, Andy.
Ciao.
Bye, Brillia.
Ciao, ciao. We're going to see each other again. We're going to see everybody here is going to be.
Absolutely. I'm desperate.
Absolutely. Yeah, desperate. We are all. Mm-hmm. Yes, we are all. Okay, but we will win. Okay. Bye-bye.
Bye. See you.
Bye, Andy. Nice to see you.
Nice to see you. Enjoy the poster session.
Yeah.
Okay, thank you.
We'll see you soon. Ciao.
Ciao, Andy.
Right, stop that.
Então, pessoal, agora a gente tem a sessão de pôster, né, até às 5 horas. Então, depois das 5, às 5 horas a gente volta aqui para a sessão de encerramento. E então, lembrem-se aquela ideia de que todos entrem aqui no Zoom para a gente tentar tirar uma foto de todo mundo. Obrigado aí pela participação, foi muito interessante. E nos vemos aí na sessão de pôster, então. Aproveitem, tem muitos trabalhos interessantes, vamos participar de sessão, assistir os vídeos e contactar os apresentadores. Grande abraço, até daqui a pouco.